To the other talk I gave 2 days ago, which was about a linker, the all famous LD program. And well, where it's relevant, I briefly repeat the important parts of the other talk. So what are syscalls? Essentially, they're functions that exist and provided by the operating system kernel. And the reason for their existence in that place instead of, say, a library or just functions that people write themselves is, first of all, that the work that they have to do require higher privilege levels than the user processes normally have, such as changing memory mappings or accessing data structures which reside in the hardware which is not directly available to the user space. So usually, how do they work? Well, again, it's a function call. So the tiny little difference is that how the actual privilege elevation process is happening and how do we actually transfer from one address space, which is the user address space, into the kernel address space, which is usually two completely different address spaces, except for typical i386 implementation where lots of operating system actually sharing the same address space between userland and kernel, because otherwise it incurs serious performance penalties. So what do system calls usually operate on? Well, files which are stored in the file systems, or sockets which are used to communicate outside or inside the machine, even pipes and other IPCs. The funny part is that all these basically 4 types of objects, they all represented by one integer, which is the file descriptor. And the funny part that historically, for some unknown reason, they grew up to have completely separate sets of operations which only apply to certain file type of objects, such as you cannot basically send to and receive from a file, and technically you can read write on a socket, but that's why there is receive and send system calls. And then to get a file descriptor, you need to open or create the system call, and to get a pipe, you need the pipe system call, which gives you 2 file descriptors instead of 1. And for IPC, it's a whole other set of syscalls which were created later in System 5 development. So basically, this means that we have 4 times more system calls than we really should have, where the basic idea in the good old Unix times was that there is one file descriptor that we can do whatever we want, and the only difference is how we obtain it. And this again creates another redundancy where operating on files, we can operate either using the file descriptors or by using the whole path name. Therefore, we have, again, twice more system calls than we really need. We have a stat and fstat and chmod, fchmod, and chown, fchown, and all, and even more. We have lchown, lchmod, which operate specifically on the symlinks. So this problem basically comes from the fact that the open system call was kind of left with the one little deficiency. You can open any, say, file system object which is represented by some name, except you are required to have an intention of accessing it. So basically, you cannot open the file without having a permission to read it, at least, from the file descriptor, which means instead of having, for example, just one stat syscall, or fstat basically, which operates only on the file descriptor, we cannot just open the file, because that would require a read permission from the file, where technically the intention of open system call, as it is documented and in POSIX also, is simply to map from the path name into file descriptor. So theoretically, we should be allowed to have a file descriptor which we cannot read, cannot write, but we can change the permission zones, such as we open the file descriptor which on the file which we cannot read, then we can chmod it, and then we can read it, or chmod it to write, and then we can write it by upgrading the permissions on it. So this again basically triples the amount of syscalls that exist there. Yo. To the metadata. But basically, that's the problem. We cannot use the same OpenSyscall because technically POSIX doesn't allow accessless opens. They do not specifically allow to do an open without read or read-write flags.
Yes, but it would change it just
by making a new system call, yes. Yeah. So make even more of them. That also actually cannot work because the access flags, the read-only, write-only, or read-write, they are not specified to be a bit mask. So specifying read-only plus write-only doesn't mean it's the same as a read-write flag. And even more, historical behavior is that the read-only flag is basically 0. So if you don't specify anything, of course, it's not the case in many modern operating systems. I think BSD is the only case left on the planet that still has read-only 0.
What about an additional flag? So open just for stacking manipulation and not access. Something like open no access.
Yes, that semantically, technically it is of course possible. But semantically that still creates kind of wacky problems. First of all, well, if you make a new flag, then you have to make people use it. So then in other systems, people will create another flag because there is no one person who can go and say like, you all change your open system call. So everybody will start doing it differently as it historically has been happening forever. So everybody has tiny little flags which are sometimes even completely opposite meanings, but doing the same stuff except they're reversed in different systems, Linux or BSD or Windows or whatever, Sun, Solaris before. So technically it's much easier to abuse. For example, there is a very good candidate, asynchronous I/O API, which is specified by the POSIX, specify read-write and all the funny stuff, but it doesn't specify open. There was a huge discussion for, I think, many years if the asynchronous open actually makes sense. But one place where it makes sense is where, one, it's not specified by the POSIX, therefore anybody who implements it can do whatever they want, such as introducing accessless opens, where you can then obtain a file descriptor and you can do IOCTLs, for example, or some IOCTLs, or changing metadata on the file descriptor or things like this, or just pass it to somebody else and elevate the access rights depending on your program architecture. But modifying open is actually, I discussed it with several people, and it's really dangerous to modify existing open. First of all, it already has like 10,000 different flags, and half of them is different between every operating system. So this is kind of shaky ground. So of course, over time, people thought like, okay, syscalls are not enough, let's invent other more awesome ways to access data from the kernel, because creating system call to access just every tiny little variable from the kernel sounded like overkill. So there was the KVM mechanism, which is basically kernel virtual memory mapping, where the user process can map a piece of kernel space and touch the variables and everything. Of course, this has a problem because once you mapped it, first of all, to map it, you have to be root, but once you mapped it, you might as well map it writable, And there you can modify the kernel behavior not only for your process, but for anything else, therefore completely violating the whole concept of access control that Unix kernel is supposed to provide. So, of course, that was not enough, and on top of all good old IOCTL system call, they grew up at the FCNTL, which basically half of it is doing the same thing that could be done with IOCTLs or anything else. And then again, for sockets, there is a get set sockopt, which is only for some magical reason applicable to sockets. Why not just have, say, IOCTLs where that modify the socket options, parameters, whatever, buffer sizes. And of course, that was not enough, so people invented sysctl, which is another awesome way to access kernel variables. Of course, when they did that, they forgot the reason why KVM was so bad. They forgot the access control. So again, to do any sysctl in basically any BSD system historically, you have to be root, which means, again, you can modify anything except the only one variable that you're interested in. This actually partially was fixed in NetBSD several, or even many years ago. Was work for Andrew Brown, I think. Basically what he did, you can attach permissions, ownership to sysctl variables by dynamically creating them at boot time. Well, of course, that completely duplicates the whole concept, again, of the file system that has all these attributes there already, and perhaps these variables could be instead the files in the file system. Of course, that was not enough again, and people invented system architecture system call, which is generic system call, which allows to pass some magic arguments down, way down to the back end of the operating system for every different architecture, such as, for example, enabling or modifying the MTR memory register, memory region registers, or any other funky i386 features, or whatever exists on other CPUs. And on top of that, of course, there is a magic syscall pathconf, which is even part of the POSIX, which is, again, duplicating the whole idea of just having, for example, one IOCTL as it was intended in the old-time Unix times. So why is it all such a big fuss about it? First of all these different ways of doing the same thing, and lots of them actually overlapping the functionality, they come through completely different code paths, which means the same functionality has to be implemented slightly different in every code path, which means every code path have different bugs. And even more, it has been proven in case of sysctl, for example, in BSD systems, where there were missing rain checks for the buffers being passed in and out, where the normal syscall path for doing similar things actually did the rain checking, but the sysctl path was staying there for 10, 20 years since the last 4.4 BSD, and nobody ever looked at it. And then suddenly, oh, wait a minute, and it's a completely parallel code path, which is implementing similar things that something else does, and people just forget to fix it all the time. So by having multiple similar access methods, we are creating problems for ourselves. And of course, the more different access methods they have, and more even syscalls we have, the more possibilities we have to abuse it for our purposes. Such as, for example, the typical, again, the return to libc attack, where we have to guess the function addresses from libc, such as syscall wrappers. And in case of, say, randomly mapped libc and or even spread out functions all over the address space, if we have 300 system calls, we have to hold 300 places we can check for. And if we would have had, say, 100 system calls, we have much smaller space to hit, which would make it harder. Of course, it's only 2 bits, but 2 bits on top of 16 bits on top of another 2 bits eventually helps a little bit. And again, since we have, for example, all these syscalls, and we have a randomized libraries which contain the syscall wrappers. And why do we have to, first of all, guess the whole address space layout and try to figure out where the syscall wrappers are if we can just use our own wrappers and our direct system calls directly in our exploit code, which would basically save us the whole work of guessing where the entry points are. And or, for example, by having just guessing one syscall, we can abuse the part of the syscall wrapper, half of it basically, to do any syscalls, because as we will see later, syscall is basically a trap which loads a register with the syscall number. So we can as well, instead of branching in the beginning of the wrapper, we can branch directly to the trap instruction if we can guess the address space for sure. So how this brings us to the point how they actually usually implement it. So on most of the architectures, starting, well, before VAX on PDP-11, it was similar as well, but for the purposes of 32-bit operating system, we start with VAX. It was a trap, which is basically an interruption of sorts that transfers control to the kernel, elevating the privilege level. So some sort of descriptor in the i386 world, it's a gateway which is one slot in the interrupt descriptor table, specifies what is the target privilege level is going to be. So the user runs usually with 3, the kernel runs with 0, and on almost all the Unix systems it was the same since they've been there, Unixes, because basically every CPU that has been used for Unix implements syscalls through a trap. There is slightly difference on MD64, for example, where it's not a standard trap, but it's a magic register in the CPU where you put the address of your syscall treatment function, which is get called when you call the instruction syscall. But basically, it's just another trap, just differently organized. And another thing on i386 is the funny C-center instruction, which doesn't cause complete context switch and allows the actual wrapper in the kernel to decide which registers to save and everything. But basically, in practice, that meant to save some CPU cycles, but that doesn't really help that much. And essentially, it's the same trap anyway. So there is one funny architecture, however, the HPPA RISC. It's dead architecture anyway, but there is one funny thing that they figured out for some reason. Of course, being a completely closed architecture, it's unknown why they designed it this way. But the privilege elevation process is actually 2 branches. Instead of having one trap, one has to branch to the special page, which is mapped specially for the kernel, and there is exactly to one instruction on that page which will elevate the privileges. This has a very funny application, which basically means our system call entry into the kernel doesn't have to be anyhow fixed in this case, which means the attacker who creating his own code and prefers to do syscalls by hand, by himself or herself, cannot really do it directly. They still have to guess the address of the magic page that actually creates the privilege elevation. And this sort of gave an idea of why we cannot do it on basically every architecture. So instead of having just a wrapper, which is typically 5, 10 instructions, whatever, that loads the register with the syscall number, do a trap, on return do a error checking and return back to the user, we again split it in half. We have the syscall wrapper and we have a trampoline, which is a magic page. And which is a magic page, which is, this is kind of sequence that you would do instead. So instead of doing trap directly, the syscall function jumps to the magic location, which was previously specified by the kernel and fixed in the program, which we will figure out later how it happens. and jumps to the magic page, and that page makes actual trap. This has gives us a possibility for the kernel, which knows where the trampoline page is, to check where the actual entrance to the syscall happened from. So if, for example, we are running a exploited stack buffer on the stack and running code on the stack which does its own system call traps, in this case it will be immediately detected because the trap for the actual system call comes not from the magic page which it's supposed to come from, but it comes from some other address. In which case, we can produce a very meaningful log message, such as the syscall comes from blah, and it gives you a hint that perhaps you're being attacked. And the second half is basically it's immediate death. Instead of where you might be running the exploited code from stack, it might actually survive for a while before it steps on unmapped memory or does some wrong stuff. So this basically allows us to control who and how can elevate the privilege level when they enter the kernel through the system call. And because basically the address of the trampoline page is the cookie, we can always control it if the user is actually using the righteous cookie that we gave them before. This is somewhat similar to how the randomized signal trampolines are implemented on systems that actually have the kernel provided signal trampolines, which are usually randomly mapped. The only difference is that the signal trampoline, the user process doesn't have to know the address of, because it's only the kernel who does the signal delivery. In this case, we have to pass the cookie from the kernel to the executable, which has to patch this cookie address into the syscall wrappers, which is, again, the less of them we have, the less work to do would be. So how we basically deal with the cookie? The first thing is, say, dynamically linked binaries, which means that we have a libc which is dynamically linked, which means it has the PLT table, which which contains one entry per each function in the libc for the outside program to call these functions. So when we start up the program, when the LDSO maps the libc, it can simply go and punch the cookie into the PLT entry for the system call handler. So this still provides us with a slight weakness, because now the attacker, instead of fishing for syscalls, he can fish for the PLT and find in the PLT where the syscall entry is. So it's still a sort of information leakage. And for static linked binaries, the situation is different, because first of all, static linked binaries will not have all the entry points for all syscalls in the libc. They will only have entry points for the syscalls that is being used. But on the other hand, instead of punching just one indirect reference in the PLT, we have to go and fix all the syscall wrappers. Because again, if we use one global variable, that creates a possibility. Because again, the global variable is much easier to fish for than, say, dynamically allocate memory. So that would create a little slack for the attacker, so it's easier to fix the code on the startup time. And so basically this code is not production finished. Right now it exists as two parts of proof of concept. One part, linker punching, fixing the addresses, which is done by basically injecting the undefined symbol into the symbol table at the link time, and then at the loading time, the LDSO fixes the undefined variable with the syscall address, and then the PLT gets fixed automatically. And for static binaries, there is a little bit more work. It's the part I talked about in the other linker talk. Is basically it requires sort of dynamically at the loading time going and fixing the code references for every syscall. Then again, the less syscalls we would have, the less work there is, and there is less possibilities for attacker to fish for the addresses, especially when it's all randomized. So I hope perhaps in the next 1 or 2 weeks I'll finish it up and it will be production quality. Yep. This is the idea. You?
Yes, so one question. When the uses enter methodology is introduced in Linux or with syscall syscall instruction, there was this small issue where this virtual network mapping VDSO has been created by the kernel, where there are a couple of low operations after the syscall, where Linus Thomas just wrote he feels like a dirty jit, and Dijkstra will runs it in his brain because he dirty tricks, because it was really some very crazy stuff required with goes and jumps, just not for calling this but for the return from this call.
Yep.
How does this interfere with your two-step trampoline?
Well, basically, the trampoline page has also a slight advantage that basically the actual syscall entrance and immediate return is the code, these few instructions, are actually provided by the kernel. So, for example, it could be modified for different CPU types, or it could be modified for different syscall entry return mechanisms. So, for example, we don't have to always stick to the trap, the int80 old entrance. Sometimes we might use ccenter, or sometimes we can use the int trap, depending, for example, on the binary. Like on BSD, there are compatibility layers. So if we figure out we are running Linux binary, we can provide the sys trampoline page like this and for other. But basically, again, it's the code that provided by the kernel. Therefore, we know how to arrange it, and even more. First of all, we can cheat, and the stupid system calls like getPid, for example, which is simply returning the integer, we can punch directly in the page. It's a whole page. We can stuff a lot of things in there. Or get time of day, for example. If we would have a global time variable, as lots of operating systems usually have in the kernel somewhere, we can as well maintain a copy of it, or just copy it in the page and then return without switching completely the context and the modifying registers and everything. And another little thingy that we can do with trampoline page is actually say it's randomized. So we only have, well, 32 bits. Of course, we cannot randomize all of them, or even the upper part. So usually it's 16 bits above the page address. And 16 bits is not that huge amount of entropy to guess. So what we can do is we can duplicate the syscall entrance return path, say 8 or 16 instructions, all over the page, and then use the offset in the page as an additional part of the cookie, which means well, let's say if it's 16 bits, that's another 8 bits of entropy, which gives us basically 24 bits of entropy, which is much harder to guess for the attacker, especially in this case. Most likely he or she will be dying every time they trying to guess, or every few times. So it's basically making it really impossible to just guess this part. So yeah, so to reply to your original question, basically we can do anything we want. And again, it's in the kernel, so we don't have to recompile the userland. We don't have to modify or even check the CPU type or anything like this. Yeah, it's a page that on startup of the process get mapped in the address space. So in a very simple case, it's one physical page with simply duplicated code, which is mapped to everybody. Of course, this doesn't allow us to do getPid, for example, or makes getPid much more complicated. So instead, we can say, okay, we make one page copy for every process, and then every process can has their own getPid version, which is one instruction and return. One check, jump, load the register, return. Just as a tiny little optimization, because, for example, why getPid is very important for, in this case, is lots of functions in the libc use getPid as an indicator if the process has been forked, such as malloc and the arc4 random, well, in the BSD kernels, to reseed the arc4 for every new process. So basically, every time you're calling arc4 random to get 32 bits of randomness, which technically is very, very tiny operation. It's about 2 memory stores and a couple of register loads. But if you add on top of that a get PID, it immediately becomes a huge thing. So doing arg4 random just to fill up the huge pieces of data becomes very slow process, just because we have to do a get PID to check if we accidentally forked somewhere. So get PID becomes very useful, optimized like this, because it, instead of becoming a full-blown syscall, it becomes basically 5 instructions or whatever. But Linux, I think, does similar things already for get time of day, get PID, and get to eat and things like this. But again, having a trampoline page, which is again provided by the kernel, we can control this stuff. We can say, yes, screw the get PID. We just give you a plain gateway page for trapping into the kernel, and we don't optimize the syscall, or sometime later in the future we decide to do it, and we can still do it. It's transparent. You. No more questions? Thank you then.